Good morning, everyone. I'm Devika. I'm a assistant professor from the Department of Electrical and Electronics Engineering at Sri Muthugunda Institute of Technology. Today, we have learned about the subject on MR3452 Control Systems Engineering. It's the regulation 2021. Now, we are going to see the topic on mechanical systems. So, mechanical systems are systems that involve motion of physical components. These systems can move in different ways and commonly used in machines and engineering applications. There are two main types of motion, uh, translational motion, rotational motions. These systems are widely used in machines and engineering applications. Translational system. The translation system is a system in which all parts move in a straight line. So the motion occurs in the same direction for all components. Examples: moving elevator, a sliding block, piston in a slide cylinder. These systems are very common in mechanical and control applications. Then components of translation system. The main components of translation systems are mass M, spring denoted as K, damper is denoted as D, external force denoted as F. So mass means it resists the motion due to inertia. Spring, it stores energy. Damper or dashpot means it dissipates energy and reduces vibration. External force causes the motion. Each component affects the system's dynamic behavior. Then equation of motion in translation system. Based on Newton's second law, the equation of motion is F is equal to m d square x divided by dt square plus b dx divided by dt plus kx, where x is a displacement. The rate of change of displacement is called velocity. The rate of change of velocity is called acceleration. This equation represents the balance between applied force and opposing force. Then rotational system. A rotational system in which motion occurs about a fixed axis. All parts move in circular paths. Example, rotating shaft, electric motor, flywheel. Rotational systems are widely used in electrical machines. Then components of a rotational system. The main components of a rotational systems are moment of inertia denoted as J, torsional spring denoted as K, rotational damper that means dashpot denoted as D, torque applied torque denoted as T. So motion of inertia, it resists the angular motion. Spring, torsional spring, it stores the rotational energy. Rotational damper, it reduces the vibrations. Torque, it causes rotation. These components are similar to translational components but in angular form. Equation of motion in rotational system. Based on Newton's law for rotation, we know that the applied torque is equal to the sum of all opposing torque. So, based on according to Newton's second law, applied torque is denoted as T. Components are moment of inertia dash per K. So the equation on this system, T is equal to J d square theta divided by dt plus b into d theta divided by dt plus k into theta. Theta means angular displacement. Then rate of change of displacement is called angular velocity. Rate of change of angular velocity is called angular acceleration. This equation describes rotational system dynamics. Comparison between systems, translation and rotational systems. Um, uh, input wise, the force is input in this transit system, and torque is input in the rotational system. Components are here a mass in the translation system denoted as M, moment of inertia denoted as J in the rotational system. In translation system, the linear motion. In rotational system, angular motions. So here, the output is displacement. That means denoted as x. In rotational system, the output is angular displacement denoted as d theta. So both the systems are mathematically similar. Applications of both systems. In translation systems, applications that means shock observers, conveyors. In rotational system, motors, gear systems, turbines. These applications show the importance of mechanical systems in engineering. Here we have see one problem related to the translational system. So for the mechanical translation system shown in figure, here we determine the transfer function of the system. Here we have two masses, so mass 1, mass 2. So in step 1, we have to find the free body diagram of mass 1 and mass 2. Then we have to form the linear differential equation of mass 1 and mass 2. Then taking Laplace on this equation, um, so convert into S domain. So both the equations are, we have solved the both equations. These are the free body diagram of mass 1. So forces acting on mass 1, spring K1, spring damper B1, spring K2, damper B2. We know that the spring is directly proportional to the displacement. So we have to write K1 X1. In dash part is directly proportional to the velocity. So B1 X1, I mean dx1 divided by dt. X1 means the displacement of the mass 1. So that means the output of the mass 1. Spring cage is connected between the mass 1 and mass 2. So we have to write K2 into X1 minus X2. The damper, that means dashpot, B2 is connected in between two masses. So B2 into dx, dx1 minus x2 divided by dt. Using Newton's second law, we know that applied force is equal to sum of all opposing force. In mass 1, we have no forces are applied. So we have denoted as 0. So 0 is equal to sum of all opposing forces. Sum of all these values, we have get the first equation of this mass 1. Next equation of free body diagram of mass 2. Here force is acting on M2 spring K2. K2 is connected in between two masses. So now we have considered mass 2. So K2 into X1 minus X2. That means K2 spring is directly proportional to displacement. Then dashpot. Dashpot is directly proportional to rate of change of displacement. That means proportional to velocity. So we know that V2 into dx1 minus x2 divided by dt. External force is applied in mass 2. So we have denoted as F of t. So according to Newton's second law, applied force F of t is equal to the sum of all opposing force. So we have to sum of all these values. We have get the equation of mass 2. So both the equation, we have to take Laplace on this two equations. So it convert into the S domain. So we have solved these two equations. We have to find the find the transfer function of the systems. Thank you.